Okay, so today we're going to continue our discussion about the asymptotic normality of the stationary and m-dependent random variables in the sequence. So again, as a recap of what we proved last time, so this important theorem regarding this topic, that is, we have our random variables x1, x2. Hold on 1 minute, please. Sorry, give me 1 second. Oops. Okay, so basically in this theorem, we say that this random variable sequence is stationary and m-dependent. So these two are the essential conditions for this theorem to hold. And we have each random variable's mean denoted by the mu and variance equal to sigma squared. So essentially, the stationarity ensures that these random variables are IID themselves. And also the m-dependence just let us only, m-dependence simplify the, and also stationarity, those two things simplify the covariance structure of the sample mean. So this makes us only need to worry about the covariance between two random variables that are not farther apart than m sequences, m indices in the sequence. So the statement of this, or the conclusion of this theorem, is still about the root m times the sample average minus mean. This will converge in law to normal distribution with mean 0, and the variance is sigma squared plus 2 times k from 1 to m gamma k. Okay, and here where each gamma k is just the covariance of x1 and x1 plus k. That's the gamma k. So then you see, as long as you can have the mean of each variable, the variance of each variable, and the covariance, the m covariances between x1 and x1 plus something, so for k less or equal than m, then you can have the asymptotic distribution. So last time we gave you an example that applies this theorem, and it's about the mth product moment. So today we're going to do another example to show how it can be useful in practice. So in this second example, we called it as the problem of runs of successes. So what does that mean? We are in the classic setting of coin tossing. So let's say that we have x1, x2, and etc. They are IID Bernoulli with probability p. So each toss is independent of each other, and they have the same success probability p. And then we denote Tn is defined as the number of runs of successes. What does it mean? It means that we have a segment of ones. So for example, if I can have a sequence realization as 1, 0, 1, 1, 1, 0, 1, 1. Okay, if that's my sequence, then Tn here would be equal to 3. I have 3 runs of successes. So I will count the number of consecutive ones. Okay, consecutive one segments. So this is what we're interested in. And the question we want to know is, what is the asymptotic distribution of Tm if I let my n go to infinity? That is, if I keep tossing this for a long time, what would I expect the number of wrong successes to be distributed like? And the distribution is across the realization. So for example, here, in this realization, although my n is still pretty small, but you see here, Tn is 3. But if I realize it again for, let's see, here I have 8, n equals 8. So if I realize another n equals 8 sequence, I may have Tn equals 2. I may have Tn equals 5. So I'm just interested in the distribution of the Tn when n is very large. And that's what we mean by asymptotic distribution. So to do that, we need to have a mathematical definition for Tn. So how can we write Tn as a formula of x1 to xn? That's how we're going to do it. So think about how we define the a rung of successes. So if you look at this example, you can see except the first one, which just have 1 in the beginning. For the second and third, there is a very clear pattern. That is, this one is 1 and the previous one is 0. So is this one. So we must have a 0 before the next rung, so we can call it a rung. So this is the pattern we want to use to define the rung of successes. But as I said, this pattern doesn't apply to the first one, because the first one, if it's a rung, then it must be 1 by itself. So therefore, you see, with my explanation, we can have Tn written as the number, the summation for I go from 1 to n. I'm going to check an indicator whether a rung starts in the ith position. Okay, and in order to check this indicator condition, I need to consider whether I is 1 or greater than 1. So for I equals to 1, I just need to make it as x1. Because x1 is 1, then it's a rung. If it's 0, it's not a rung. And for subsequent positions, I need to check whether that position I is 1, and also whether the position before it, the I-1th position, is 0. So I need to check both. Then you see, for I go from 2 to n, I need to check whether xi is 1, right? That's itself. And whether its previous one is 0. Since it's binary, I can do 1 minus xi minus 1. Because when xi minus 1 is 0, then 1 minus it is 1. So you see, to have a 1, I need to have this equal to 1 and this equal to 1. If either of them is 0, I will not get a 1. You see, this is the definition of Tn. And with this definition of Tn, then we see some hope, because the Tn is actually a random variable plus a sum of random variables. And we know we will let the n, which is the items in the sum, to go to infinity. Then we are kind of in the similar situation to our theorem here. Because as I said, x bar, xn bar, and the summation, they only differ by a factor of n. So that's why you can have the asymptotic distribution of the sample mean, which means you also have the asymptotic distribution of the sample sum. And this is the sum. So in order to use the theorem, we need to define each item in each term in the summation to be the random variable in our sequence. So we define yi equals xi plus 1, 2 times 1 minus xi. You see, by defining it this way, because here this term goes from 2 to n, then here I go from 1 to n minus 1, right? I have those n yi. So therefore, you see, I'm interested in, so Tn can just be written as x1 plus summation I from 1 to n minus 1 yi. And then I'm going to apply the theorem to the summation of yi. So I need to know what's the mean of yi, what's the variance of yi, and what are the covariances. And also, most importantly, whether the yi sequence is stationary and m dependent. What is the m? I need to answer those questions. So first of all, let's check expectation of yi. So for this expectation of yi, by definition, is expectation of xi plus 1 minus xi, right? Because xi plus 1 and xi are independent, so we can separate the expectation by factorization. So it's exi plus 1 times 1 minus exi, right? I also get expectation into the random variable and constant get out. So you see, by the Bernoulli, this is basically p times 1 minus p. That's easy. And next, what's the variance? The variance of yi, so I will call this mu to be consistent with the notations in our theorem. The variance of yi here is, I can write it as expectation of yi squared minus square of expectation of yi. The second term I already know, so I don't worry about it. How about expectation of yi squared? What is it? Look at what values yi can take. Interestingly, yi can only take 0 or 1, right? That's the only two values yi can take. And because we know 0 squared is 0, 1 squared is 1. So that's why expectation of yi squared is just expectation of yi. And I can write it as this. So you see, I will get p times 1 minus p squared times 1 minus p squared. That's the sigma square. Okay, now the covariances. Let's look at the sequence and see how each yi's are dependent of each other. So we can have, let me write the sequence for your information. y1, y2, y3. Let's write the first three. And this is equal to x2, 1 minus x1. This is equal to x3, 1 minus x2. And this is equal to x4, 1 minus x3. So seeing the pattern, you will realize that here the dependence only happens between two adjacent ones, two adjacent yi's. If two yi's are differ by 2 positions, then they are not dependent. So therefore, we see this is a stationary, and the stationarity comes from the fact that xi's are IID and m equals 1 dependent. Okay, so here m is only equal to 1. And that is nice because realizing that m is equal to 1, coming back to the theorem, I only have one gamma to calculate. That's gamma 1. Okay, so then gamma 1 is the covariance of y1 and y2. Okay, and I can just use this definition or the way to calculate covariance as expectation of y1, y2 minus the product of ey1 and ey2. So now let's think about y1 and y2. What is the product? What values can this product of y1, y2 take? So you can see there's a special dependence here because x2 is involved in both y1 and y2. And we know that when x2 is 1, here 1 minus x2 will be 0. So therefore, you see either x2 is 0 or 1 minus x2 is 0. And then either y1 is 0 or y2 is 0. So that's why y1 and y2 is equal to 0 with probability 1. So this is equal to 0. So therefore, we can get rid of the first term, and we only have the second term, okay? And the second term, because EY1 is equal to EI2 by IID, so I will have this as negative p squared 1 minus p squared. That's it. Then finally, by the theorem, I'm going to apply that. I would have root n times summation, root n minus 1 to be exact. It should be root n minus 1, I from 1 to n minus 1 yi over n minus 1. That's the sample average minus the mean is the mu, okay? Minus the mu, converge in law to normal distribution, mean 0. In the variance part is sigma squared plus 2 times gamma 1. And I have everything calculated. I just need to plug them in. That's it. Okay, so you see, I get the asymptotic distribution of this. Then finally, I want to replace this by Tn. Okay, so you see, I want to do is replace the sum by Tn minus x1. Okay, and I would have n minus 1. This is Tn minus x1 plus minus mu. Okay, they are equal. But here I can do some simplification because I know x1 is binary, either 0 or 1. So therefore, the term x1 over n minus 1 is going down to 0 as n go to infinity. So this term I don't need to worry about. This x1 over n minus 1 is diminishing. And another thing I can simplify is this. So that is the Tn, right? The Tn here is, oh, sorry, no, not Tn, the n minus 1 and n minus 1 here. When n is large, asymptotically, I can replace n minus 1 by n. So therefore, by doing those simplification, I would have root n times Tn over n minus mu converge in law to this normal distribution. That's it. So that's how we derive the asymptotic distribution for the number of runs. So for those of you who are interested in this, I think you can play with a simulation to see how good approximation is. Now with computer, you can do that. How would you do it? You basically just randomly draw n Bernoulli random variables as n1 to x, as x1 to xn. And you can set the n to be large. Let's say probably you can set n to be 100. That's not so large number nowadays, but in the old days, that's considered to be pretty large. You can set n equals 100. And for the 100 variables, you can simulate them for many times. Let's say you simulate them for 1,000 times. Then each time you can count the number of the number of runs of successes in that sequence. So you will have 1,000 values for Tn, and then you can plot the empirical distribution of your 1,000 values using a histogram. You can plot this Gaussian density curve, and then you see how well they match each other. I think that's a way for you to see how the asymptotics works, how well it works now in practice. So yeah, play with the simulation if you're interested. I think, so with computer, I think it's a very useful learning tool because you can realize, you can see the numbers. Previously, in those days, the mathematicians, the probabilists, they can only realize those in their minds, but now you can realize them on your computer. And I think that can make the learning a lot more intuitive. Okay. So finally, we want to make some last note about the interestingness of central limit theorem. So this is what we called the central limit theorems. How well is the approximation? Is the normal asymptotic normal distribution approximating the actual distribution of sample average? So this is something we called the Berry-Essen theorem. But please make a note that here, all the discussion here is about random variables that are one-dimensional. So this is called the univariate extensions of the CLT. So don't worry about the vectors here, x1 to xn, they are one-dimensional. And the first thing we're going to talk about is called the Berry-Essen theorem. This is a very, very interesting result, very clean result. It tells us that so for the approximation of the sample average distribution by the normal asymptotic normal distribution, the error, right, the approximation error is actually determined by, of course, sample size, and also by the third moment of your random variable. Okay, so basically, let's say that we have the x1, x2 to xn, and so on. So here they are IID. And I gave you the notation as always. So mu is their expectation. Sigma square is the variance. And here I also define a thing which I call the third moment. So we will just use this notation rho to define as the third center moment. So here x1 minus mu, absolute value cubic. So, this is what people call the skewness. This is the skewness of a distribution. Actually, no, sorry, my bad. I think that's not a skewness. The skewness here is the, right, the skewness should be, sorry, not absolute value, my bad. I should cross this out. So I should just write here, skewness is defined as expectation of x1 minus mu cubic, but no absolute value. But here we have the absolute value, my bad. Yeah, so that's why the skewness could be 0 if your distribution is centered around, is asymmetric around mu. But here it's not actually the skewness, it's the absolute third moment. So what the Berry-Essen is saying that if you define, let this Gn be the CDF, cumulative distribution function of this statistic or random variable, that is root n times, let me see, root n times xm bar minus mu divided by sigma. Okay, so I'm basically taking the sample average and center it and then standardize it. And then I multiply by root n. So in other words, when I say the CDF, it means that Gnx is defined as the probability that this random variable root m xm bar minus mu, sigma is less or equal than x. That's what we mean by the CDF. And then, by central limit theorem, right? CLT tells us that this Gnx is convergent to the normal CDF. the standard normal CDF. This converges pointwisely for all x in R. And this is the CDF of standard normal. This is exactly what the CLT tells us. And the Berry-Essen is telling us how well the approximation is. And also, furthermore, I want to say that this can also be written as uniform convergence, not just point-wise convergence. The reason is because these two things are both CDFs and they're bounded. Their values are bounded between 0 and 1. So by boundedness, I can actually strengthen this convergence as sup x gnx minus phi x. This is going to 0 as n go to infinity. So we can strengthen it this way. And why is that? So what is the difference between the uniform convergence and the pointwise convergence? If you recall, we briefly talked about this when we talk about the Glivenko-Cantelli theorem, which is regarding the convergence of the empirical CDF to the population CDF, right? That's the Glivenko-Cantelli. And here, it's the similar argument. So when we say uniform convergence, we mean that given an epsilon, that's a very small error. Given the epsilon, the neighborhood size in X, delta, that neighborhood size, here it may depend on the X, and here it doesn't depend on X. So that's very important distinction between the two convergence. So that's why this implies that, but may not be vice versa. Okay, and this is CLT, but the Berry-Essen give us a fine result about how well can we use phi to approximate GM. So Berry-Essen can be written as the sup x of the difference gnx minus phi x. This sup difference is upper bounded by a constant c times rho, this absolute third moment, divided by sigma 3. So sigma 3 is sigma square, take square root first and then cubic, right? It's a standard deviation of xi to the cube times root n. So this is a very interesting result because, you know, the constant is not depending on the distribution of x1 to xn. This is a constant. And the most recent constant people have derived is actually, you can regard it as approximately 1/2. So this is a pretty small number now. You can take it as 1/2. And for this one, the rho and sigma cube, those two things depend on the distribution of your random variable. So in other words, you see that the approximation can be better or worse depending on how the original distribution of your random variable is. So it's not the same level for all random variables. And especially if the distribution of your random variable is very well concentrated around its mean, which will make the rho very small. And in that case, the approximation will be even better. But regarding n, we see this upper bound is diminishing at the rate of root n. So it goes down at the rate of root n. So these are all the important insights we learned from Berry-Essen. And one more thing, I think it's a related topic, but it's not really about the central limit theorem. It's just a related thing that came to my mind. I think it's worth mentioning. I don't know how many of you have heard of it. So it's regarding the approximation of a normal CDF, or I should say the tail probability of a standard normal distribution by the density of the standard normal distribution. So how many of you have heard of that? So how can I set an upper bound on the tail probability, right tail probability of a normal CDF?
Is this like value at risk that you're referring to? or
What do you
something,
mean
or
by
is it
that?
related to that?
So maybe I can write it down. So it's better if I write it down. So what came to my mind is that if you have this random variable z that follows standard normal, then if I'm interested in, let's say, a t greater than 0, if I'm interested in the probability that z greater than t, how can we approximate this? You know, exactly we need to do the integration, t from infinity and phi z dz, right? And where the phi is the CDF, is the PDF density of the standard normal, right? When we want to be exact, we have to do the integration. But this doesn't give us a closed form formula. So even though now we can do we can use computer to get an approximate thing we can do this calculation, but we cannot really write it out in terms of t, in terms of lowercase t. So here we want to just give it an approximation. And this is a very fun thing to know. So we can actually have an upper bound and the lower bound to bound this tail probability just based on the PDF. And in fact, this is upper bound by phi t times phi t divided by t. So it's 1 over t times the phi t. And this other end, it can be written as 1 over t minus 1 over t cubed phi t. So you see, you're basically bounded using some closed form formula, because the closed form is from the PDF, and the PDF we know its formula, right? It's exponential to the negative 1 over root 2 pi times exponential to the negative xt squared over 2. So we have that. So this is very convenient to use if you want to do it. Yeah. And furthermore, you know, as I said, so this side I can write it as 1 over root 2 pi t times exponential to the negative t squared over 2. Okay, so that's why this is quite convenient to be used. And furthermore, so in many cases, because you know this t can be very, very large, right? When t is very large, you can have this root 2 pi times t to be larger than 2. That's easy to achieve. So therefore, when t is large, you can actually safely say that, okay, this probability, this tail probability can just be upper bound by, let's say, 1 over 2. So then that's even easier because you can get rid of the t from here. So I'm just saying that this is related, but it's not really about what we're trying to talk about in Berry-Essen. This is just a useful thing to know if you want to find the tail probability bound for a standard normal distribution. That's it.
Hi, Professor. Are these bounds very tight, like the lower bound and upper bound?
I would say yes, because you can imagine that if your t is very large, then the difference between this and the 1 over t minus 1 over t cubed, this will be so this term will be very similar to 1 over t if t is very large.
Okay.
And because we have a lower bound and we have an upper bound, so it's actually in the middle.
Okay, thank you.
Yeah. And I think the key thing is always to think about this term, right? This exponential term is the dominating term. We know that as t goes up, this one dominates how fast you can decrease. So that's why we can approximately say this is how fast this tail probability is decreasing. Okay. And so that's just the Berry-Essen. And a related thing is what we call the Edgeworth expansion. So I'm going to be quick about this. I think it's just something it's good to know. So the Edgeworth expansion, this is related to, in classic statistics, what people call the higher order asymptotics. So what this means is that we call the asymptotic distribution. We derive that. So the root n, this one, the root n times this, the CDF is this by GM. We say the approximation of GM by standard normal is a first order asymptotics. Okay, so and then if we want to go further and further, we can say we have a second order, third order, etc. So essentially, the expansion, I'm going to write it out quickly. It's just as for the GNX, we write as phi x and the term. So the term is gamma x squared minus 1, 6 root n, phi x, and minus, we have another big term here, but the detail is not so important. I'm just copying it. Tau x cubed minus 3x, 24n plus gamma squared x5 minus 10x cubed plus 15x, 72n. Okay, phi x. And finally, we have a remainder that's small o 1 over n. Because this term is on the order of 1 over n, this term is on the order of 1 over root n. Okay, so what are gamma and tau? So here, basically, we have, let's say if we define this yi, okay, I just defined this as the standardized version first, xi minus mu over sigma. This is a standardized random variable. Then I would say, then the gn is the CDF of root n times yn bar, right? The average. That's exactly what we said before. And we call the gamma as the expectation of yi cubed. This is the skewness. And we have gamma as the expectation of yi fourth. This is what we call kurtosis. So you see, both are related to the original distribution of xi. And the skewness is here, the kurtosis is here, and the skewness square is here. So basically, you see that for the Edgeworth expansion tells us if the original distribution is simpler, that means its skewness, if it's 0, then symmetric, right? If it's symmetric, then this term goes away. We directly go to the 1 over n term. So it's a better approximation. So the message is that if xi has symmetric distribution, then gamma is 0. And then we have gnx equals phi x plus a big O 1 over n term. That's what we first learned. So we just skip this 1 over root n term. And furthermore, you see the kurtosis is always here in this term. So the smaller the kurtosis, the better. But I want to say that, I want to make a caution that this expansion, as we said in our first lecture, when we use the term small o, we are basically thinking about things asymptotically. So in this simplification, so to write it this way, we actually assume n is very large. So that's why we are doing a lot of simplification to make this expansion hold in asymptotics. But what this means is that if your n is really small, it does not necessarily mean that, okay, you go further term is better than just using this first order, just using this normal approximation. So that's the key message. So this expansion is asymptotic. Okay, so it only works well when n is large. And for small n, it may not be better than just using the phi alone. So for small n, the approximation by including more terms may not be better than this phi x alone. That's the key message. So just be aware that everything is asymptotic when n is large. Okay, so that's all I want to say about central limit theorem. So we basically concluded the fundamental things we need, the techniques we need for distribution in law regarding central limit theorem. But here I want to say more about the distribution in law, which is a very useful technique in practice. And we're going to use this, probably the most common one. You're going to use this again and again. And this is what we call the Slotsky theorem. Slutsky, S-L-U-T-S-K-Y. The Slutsky theorem is about transformations and combinations of random variables in terms of their distribution or convergence in law. That's what it is. So it's about
I'm sorry, Professor.
Yeah.
I'm just curious, for the fact you mentioned before the Edgeworth expansion about just the bound on the upper tail probability of a normal variable, you didn't mention like how one would prove that. Is that something we should think about, or is it easy or really difficult?
I think it's regarding how you can basically approximate that integration. That's it.
Okay.
Yeah, but you can check it out. I think it has a name. It's called a May's inequality. It's a pretty classical result. I just mentioned for fun. I don't want to mention this as a key part of this class because it has nothing to do with our asymptotics or random variables. It's just a mathematical fact. Yeah.
Okay. Thank you.
So, yeah. So the Slotsky theorem. So it's about convergence in law for transformed variable for transformed random variable or combinations of random variables. Combinations of random variables. That's Slutsky theorem. So that's why it's so useful. And here we're going to give 3 statements for it. The first one, we call it continuous mapping theorem. Yeah, so maybe back to your question, Zach, I can mark it here. So if you want to look into this, this is called May's inequality. Yeah, you can check it out.
Thank you.
And so for the continuous mapping theorem, it's basically saying this. Okay, so if I have, then this can be applied to multidimensional random vectors. So if I have xn as d-dimensional random vector and xn converge in law to another random vector x. And this is about the condition, right? Condition 1. And condition 2 is if f is a map, is a function that maps from d-dimensional to k-dimensional such that this limit random vector is in the continuity set of F. We used this notation before. It's in the continuity set of F with probability 1. So CF is the continuity set of F. So where F is continuous at, then we would have Fxn converging law to Fx. That's why we call it continuous mapping theorem. We basically map Xn to the k-dimensional space. We map X to the k-dimensional space, but still we have the convergence in law. Okay, so for this part, maybe we can prove each one by one. That can make our understanding easier. So to prove this one, we are going to use something we learned a while ago, the Haliburt theorem. That's a very fundamental theorem for proving convergence in law. So we just let G to be defined as a function that maps from Rk to R. And we let it be bounded and continuous. That's actually the second the Haliburt, we know we have 3G, right? This is the second type of G, bounded and continuous. Okay, so by Haliburt, we just need to prove that we have the convergence of the expected G applied to this. It's sufficient to prove this expected of G of Fxn converge to expectation of G of Fx. Okay, that's what we're going to show by Haliburt. It's sufficient to show this. And then we're going to apply the condition we have regarding the convergence of Xn to X to show this. So we're going to apply Haliburt for another direction. Okay, so we define Hx to be G Fx. Okay, by this definition, then you can see H basically maps from Rd to R, right? It's a composite function. And furthermore, we have what? We have about the continuity set, right? So we know H by the definition as a composite of G and F, and G is bounded and continuous. Then every continuity point of every continuity point of F must be a continuity point of H because G itself is continuous. So in other words, we have the continuity set of F. It's from Rd, it's in Rd. The set is a subset of Rd. Is contained in the continuity set of H. The reason is that as long as F is continuous at a point, Rd point, then by G being continuous, H must be continuous at that point also. So therefore, you see that we can have, so the probability that X is in the continuity set of H is equal to 1. This is because we have this. And then we can have Haliburt by Haliburt. So that's from the one direction. So we have the xn converge in law to x, this can tell us that we have the expectation of hxn converge to expectation of hx. This is one direction Haliburt. And here, because we say that the h may not necessarily be continuous anywhere. So that's why we need this condition to help us, right? We need this to get the Haliburt through. And now you see, this is equivalent to expectation of g of fxm converge to expectation of g of fx, right? And now we only worry about g. G by our definition is any function that's bounded and continuous. Then by the other Haliburt direction, so this is Haliburt again, we have fx and converge in law to fx. So this is for any g bounded and continuous, right? So you see that here we basically apply the Haliburt for two directions, then we prove it. And that's very convenient because, you know, Haliburt is about, it changes the convergence in law to the convergence of expectation of some continuous function transfer random variable. Then this can allow us to play with the function, and that's how we use it. So this can naturally integrate the fact that we're going to prove the function for this f. So I hope this can give you some reminder of what the Haliburt was about. That's the first statement, continuous mapping theorem in Slotsky theorem. The second one is about the combination of two random vectors or variables as a special case. So second statement is that if we have xn converge in law to x, and we have xn minus yn converge in probability to 0. So if it's a vector, if xn and y are vector, then the 0 is a 0 vector. So it means that I have some convergence in law for xn, and I have another sequence yn, and the corresponding difference between xn and yn is going down to 0 in probability. So that means as my n goes larger and larger, the two random variable sequences become similar, more and more similar. So, you know, what I want is to say, does my yn converge to the same limit in law? Yes, that's the second statement. Then yn converge in law to x. So this is very useful because you can always use Central Limit Theorem to get this condition, for example. And then if your interested statistic is yn, as long as you can show that yn and xn, that is something like a sample average, sample mean. As long as you can show that they are asymptotically equal in probability, as n go to infinity, their difference go down to 0 in probability. Then you can say, okay, I can use the limit, the Central Limit Theorem asymptotic distribution here to ask the asymptotic distribution of my yn. So that's why this is very useful. Okay. And we almost use this. You see, we use this implicitly here. You see, eventually, I get from Central Limit Theorem, what I get is the asymptotic distribution of this. But I'm not interested in this x1. I'm only interested in this Tn over n. So basically, if you calculate their difference, they differ by approximately x1 over n minus 1. And that term is going down to 0 in probability. So this is already an application of this. Okay, how do we prove it? Again, we are going to use the Haliburt again. So another practice of Haliburt. So now we're going to use the first simplest type of G in Haliburt. We let G be continuous and vanishing outside a compact set. Actually, we can use the second type, bounded and continuous as well. So either one would work, or continuous and bounded. So what we want to do is we are going to use the uniform continuous. Okay, so yeah, so we were going to say the G is uniformly continuous. And then what it implies is that for any epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus y is less than delta, we have gx minus gy less than epsilon. Again, a refreshment of the definition of uniform continuity. So what I want to show is I want to use Haliburt. So Haliburt, well, let me just show it's sufficient to prove that the expectation of GYM is convergent to expectation of GX, right? As long as I can show that, I will have my statement. Then how do I do it? I want to use this condition and Haliburt, and then that can give me expectation of GXN converge to expectation of GX. Then I only need to play with the GYN and GXN. That's it. Okay. So what I'm going to do is that, so this G is uniformly continuous and G is bounded, right? So either one will give me a bounded G. So I can say, so this is one thing. And then I can say, and G is bounded. So for any X, I can have absolute value of GX less than B. So I can set this here. Okay, to show that, our strategy is to calculate the absolute difference between this and this. So the absolute difference expectation of GYN minus expectation of GX. This thing, I'm going to write it in two terms. So one is by the triangular inequality, I will have expectation of GYM. I'm going to drop the bracket for simplicity, minus expectation of GXN. Okay, plus expectation of GXN minus expectation of GX. Okay. So I already know that by Haliburt, this term is going to 0. So this term itself is going to 0 by Haliburt, right? Because I do have xn converging law to x. So this term, I don't need to worry about it. And for this term, I'm going to use the uniform continuity here, as well as the boundedness. So by the uniform continuity, I can consider two scenarios. One is that yn and xn are within each other by delta. And the second is that they are not within each other by delta. I just separate this into two terms. So for this term, I can write it as this times the indicator that xm minus ym is less than delta, plus the same absolute value times indicator xn and minus yn is greater or equal than delta. You see, and this term, I don't care about it. And you see, because the two indicators either of them must hold. So that's why this is an equality. And now you see, when this indicator function holds, I know xn and yn, their difference is less than delta. So I'm in the uniform continuous scenario. I know then gxn minus gyn will be less than epsilon. The absolute value difference will be less than epsilon. So yeah, so then this term will be less or equal than epsilon, and then I can write this as less than epsilon, because it's an epsilon. When this holds, this must be less than epsilon. That's it. And on the other hand, this is an indicator, but for this part, I can always bound it by 2b, right? So this is a b for each one. Gxn is less than b, gyn is less than b, absolute value. So the second term can be written as 2b. Oh, sorry, my bad. I should say this. I should add the expectation. I dropped that. I also moved the expectation to the outside. Okay, so previously expectation is inside. I get it out of expectation, and that's fine. We know that the expectation of absolute value is less or equal than the absolute value of expectation. So we have that fact as well. So for the second term, you see, once I get this thing in upper bound to b and get it out of expectation, okay, then I have expectation of indicator. That becomes a probability. So I get a probability that xn minus yn is less or equal than delta. That's it. I get this upper bound. Yep. And furthermore, you see, I have one condition that I haven't used, convergence in probability to 0. That would immediately tell me, okay, the second term, this term, is convergent to 0. Then I only have epsilon left as my upper bound of this. Since the epsilon can be set to any small positive number, I'm done. Okay, so then I want to say that this is convergent. So this whole thing is less than epsilon for any epsilon positive. And that's it. So basically, we say that, let me summarize it. Okay, so then for any epsilon greater than 0, we have the expectation gyn minus expectation gx less than epsilon as n go to infinity, because other term will go down to 0. So we can say this expectation of gyn minus expectation of gx is going down to 0 as n go to infinity. And then by Haliburt, once more, we have yn converge in law to x. That's it. So basically, what I want to say here is that if you think about convergence in probability, this indicator trick is very useful to use. This is actually probably our first time that we did this, or second time here. But if you check our previous notes carefully, you can see that we have used this technique in our previous notes before in some proofs. It's just that we may have skipped it in this class, in the lecture, to save time. But this is very useful in case that you can separate the case scenario of the relationship between xn and yn into two cases. One is that they are within a small neighborhood of each other. That can allow you to apply the continuity to make the number small. And the other case is that they are far away from each other than delta. But here, because G is bounded, we can get it out. Then this probability that they are far away from each other is going down to 0. So we can handle both terms. Okay, that's statement B. Again, it's about if you have a sequence that if you have a convergence in law, and if you have another sequence that has very small difference with the first sequence, and the difference goes down to 0 as n goes to infinity, then you can have the second sequence converge in law to the same limit. Okay, statement C of Slutsky. In statement C, it's about, I would say it's like an augmentation, okay? So if we have xn in Rd, they don't have to be the same dimension. Yn in Rk. So one can be d-dimensional, one can be k-dimensional. And if we have xn converge in law to x, yn converge in law to some constant vector, then we can have xn, yn jointly convergent to this limit in law. So in other words, we still have xn marginally converge to x, yn marginally converge to c. But now we are stacking them to get a joint distribution. And that's very surprising. And the fact we can do it is because here it's a constant c. It's not, so basically it's a point mass. Yn is convergent to a point mass in k-dimensional space. It's not a random vector. If it's a random vector, it will not work, okay? So this is a warning. So if we have yn converge to a random vector L in law, then we cannot simply do the stacking. This is wrong. Because as I said,
is there a simple counterexample for this?
I think many of you are very in a hurry. I'm going to say that actually.
Okay.
So yeah, the reason that will be my next sentence. What I want to say is that to say about joint distribution, you need to worry about the dependence. But here in our condition, there's no dependence between xn and yn at all. So we can easily construct a counterexample. I can tell you that. So for example, a counterexample is to be constructed by playing with independence. Okay, so I can say that. So let me have x1 to xn, let's say iid, okay? And they have mean equals to 0, variance equal to 1. So I don't need to worry about the standardization, okay? And then I have y at y1 to yn as well. So iid mu equals 0, sigma square equals 1. And they are independent of each other. So then I can say, okay, given this case, the root n of xn bar is converging to a random variable, let's say z, and z follows standard normal, right? This is by the CLT. I can also have root n yn bar converge in law to, let's say, z prime, which also follows 0, right? So here I can see that for sure. Actually, I can also say z. Yeah, there's nothing wrong with it. Yeah, so z is standard normal. But I cannot say this root n times xn bar yn bar converge in law to z and z. This would be wrong. And you can clearly see why. Because here I have x1 to xn independent of y1 to yn. So here, this is independent of this. So this is a two-dimensional Gaussian distribution when n is large. It's a two-dimensional Gaussian distribution that's independent. So here, the asymptotic distribution of this, the distribution of this, let me plot it, 0 here. So the distribution of this will be something like this. Just like a square, or I would say circle-like Gaussian density, if you draw data points from that. But here, it's the same z. So the distribution of this z is going to lie in this diagonal line. That will be the distribution of this. So that's why the joint distribution is never going to converge to the joint distribution, because here we have independence, here we have totally dependence. Yeah.
What if you add the condition that x and y are independent, or would that not be useful?
Not useful, right? Because like I said, when we talk about this is regarding the convergence in law. When we say convergence in law, we only say the distribution on this side is becoming like the distribution on this side, but there's no dependence between these two. So I can say this. So I can say, okay, so in this case, I can say the root n of xn bar yn bar is convergent law to z and z prime if z and z prime are independent of each other and they are normal, standard normal, right? You can say that. But it doesn't hold in general, because when we have the marginal, then z and z prime is the same thing, right? So you cannot go from the marginal to the joint. That's the key. But so essentially what I want to say here is that here you can write as z, or you can write as z prime. It doesn't matter, because it's just a symbol for standard normal distribution. Yeah. And another counterexample we have I think this is easier to understand. Another counterexample we have in the notes is this. Let me see. Right. So another thing we have in the notes is this. So another counterexample 2. I can write it down. Counterexample 2. Here we have x as uniform 0 to 1. And we define xn to be x for all n. So it's just a copy of x. And yn equals x when yn equals x if n is odd, or 1 minus x or when n is even. So you see, basically in the two sequences, I would have xn as x, 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 and yn would be x, 1 minus x, x, 1 minus x, alternating. So I have my xn and yn. And in this example, you can clearly see that my xn is converging in law to what? It's converging in law to x, right? Because it's equal. So is my yn. Yn is also converging in law to x, or x just follows uniform 0 to 1. Because you see, no matter how it's alternating, its distribution is constant. It's fixed as uniform 0 to 1. So yn is also converging in law to that. But you see, the vector xn, yn is not converging in law. It's not converging in law. It's not converging in law to this x at all. This is another thing. The reason is that if you imagine, so if you think about the sequence, okay? So the sequence I'm having, probably I think this is something I can spend a little time talking about before we finish. We're already running out of time. So still think about the realization. So maybe I just write it to this side. Okay, think about realization as always to help you understand it. Otherwise, random variables are just too abstract. So if you think about my x equal to 0.2, one draw, then my x1 is 0.2, x2 is 0.2, x3 is 0.2, and so on. My y1 is 0.2, y2 is 0.8, y3 is 0.2, and so on. So it's alternating. And so if you think about it, right? So what is, and that's one realization. And another realization, I have, let's say x equals 0.5. Not good number, 0.3. x1, 0.2, x2, 0.3, x3, 0.3, and so on. y1, 0.3, y2, 0.7, y3, 0.3. So you can imagine that when I say convergence and law, I'm looking at a far end of a large n, and then look across the values of the realizations of xn. Of course, here, the realization of xn will follow a uniform distribution because my x is drawn from a uniform distribution. Fixing an n, I look across the realizations of yn's. It also follows a uniform distribution because if n is odd, then it's just the distribution of x. If n is even, it's just a distribution of 1 minus x, but both of them follow uniform 0, 1. So that's why this is also holding. But if I look at a joint, right, the joint thing would have a problem. Here is that if I pick n happen to be odd, then yes, x and yn follows the same distribution xx. But if I pick n to be even, then x and yn will follow distribution x and 1 minus x. So it will not converge. That's the problem. I hope this is a better counterexample to help you realize that why we'll have an issue if the two limits are both random variables.
In this case, do we say xn, the joint distribution of xn and yn does not converge to any?
Yes, in this case,
Okay.
we say it doesn't converge because it's alternating. Yes.
Okay.
It's alternating between x joint distribution or x1 minus x joint distribution. Yeah. Does not converge. Okay.
So
I think we're good. So let's stop here. And when we come back next time, we're going to quickly wrap up the statement C. And then we're going to do something quite interesting, exciting. We're going to show why the T statistic, the thing we use in t-test, follows a T distribution asymptotically, follows an asymptotic normal distribution, I should say that. So that, you know, the T distribution is approaching normal distribution as the degrees of freedom gets large. So we're going to show that. We're going to show why the T statistic has asymptotic normality. It is a direct application of the Slotsky theorem. Okay, so see you next time. See you next Tuesday. Bye.